Hello, welcome to today's lecture in this series of lectures on Introduction to Quantum Physics. Two classes ago, I discussed the problem of solving Schrodinger's equation for an infinite potential well. So, we considered a potential which extends from x equal to 0 to x equal to L, but outside this region the potential is infinite, but inside this region the potential is 0, and we solved the time independent Schrodinger's equation for this potential, and we found that imposing the boundary conditions led to the energy being quantized. That is, energy is described by there are discrete energy levels, and each energy level is described by a natural number n, and En is equal to n square pi square h cross square by 2ml square. The height of the potential well there is infinite. So, there were actually an infinite number of bound states, but if you consider a bound state with a very large n, let us say n of 100 or more, we find that such a particle essentially behaves like a classical particle. It is only for smaller values of n that the quantum effects are important. We also looked at some of the symmetry considerations. We note that if you take the midpoint L by 2 and do an exchange, that is, if we make the mapping x going to L minus x, then the potential remains unchanged. It is symmetric under this transformation, and we also saw that the lowest energy state or the ground state is also has this symmetry, whereas the first excited state is antisymmetric when we make this transformation, and the second excited state is symmetric, third excited state is antisymmetric, and on the pattern keeps alternating. Equivalently, we can say the first excited state has no nodes, sorry, my mistake. The ground state has no nodes. The first excited state has one node, second excited state has two nodes, etc., etc. In this class, we will consider two other problems of great interest in physics. The previous problem we considered of infinite potential well, in some sense it is a made up problem. You never really have a potential that is infinite, but if the well is deep enough, you can approximate it to an infinite potential well. But here we consider that the depth of the, or rather the height of the potential well, it is finite. So, as in the case of infinite potential well, we say that the potential well, the well extends from x equal to 0 to x equal to L, and within this region the potential is 0. Outside, the potential is now some finite value u rather than the infinite value we considered before. So, in this case, the whole region of space minus infinity to plus infinity, it naturally divides into three regions. First is the left part from minus infinity to 0, then the potential well part from 0 to L, and then the right part going from L to infinity. And what we will try to do is to solve the Schrodinger's equation for in each of these three regions, and then we will try to see how the solutions in the three regions, they connect to each other to give us one well defined wave function. So, first let us look at this problem classically. Let us assume that the energy of the particle in the well is E. I should in principle consider two different cases. Case 1 is the energy of the particle is less than the value of the potential outside the well, in which case the particle will always be bound within the well, because it does not have enough energy to overcome the height of the potential. Other possibility is E is greater than U, in which case the particle need not be bound in the well, it can be anywhere between minus infinity to plus infinity. Such problems are classified as scattering problems, and Professor Aftab Alam will deal with those problems in the next set of lectures, but in my lectures I will confine myself to bound state problems. So, I will consider only the case where E is less than U. So, in region 1 I can write the Schrodinger's equation after some manipulation as d square psi 1 dx square is equal to 2m by h cross square multiplied by u minus e. U minus e is a positive quantity, so I define that factor on the right hand side 2m by h cross square times u minus e. I define it to be some positive constant alpha square. Now, exactly the same equation is also valid for the wave function in region 3. However, in region 2 potential is 0, therefore, the time independent Schrodinger's equation takes the form d square psi 2 by dx square is equal to minus 2me by h cross square. Mind you, here E is positive, so 2me by h cross square is positive, but there is a negative sign in front, and this quantity 2me by h cross square I define it to be some other positive constant k square. Let me remind you that strictly speaking there is one single wave function, but in region 1 it has some dependence on x which we call psi 1 x. In region 2 it has some other dependence on x which I call psi 2 x, and in region 3 it has some third dependence on x and I call that psi 3 x. But there is one wave function for the whole problem, we have to keep that in mind. We first look at psi 2. If you see the equation, we have d square psi 2 dx square is equal to minus k square psi 2. This is the same equation that we had in infinite potential well, and the solution in general is some constant times sin kx plus some other constant times cos kx. In the case of infinite potential well, we argued that the cos kx term shouldn't be there based on boundary conditions, but here the boundary conditions are different. So, we can't make the same argument as the infinite potential well, we have to keep both terms, both sin of kx as well as cos of kx. Let us look at the wave function in region 1. If you see, the equation is d square psi 1 dx square is alpha square psi 1. This has again two possible solutions. One is e power alpha x and the other is e power minus alpha x. So, I take a linear combination of the two where I have two constants a and a prime. And as I told you, exactly same equation holds for the wave function in region 3. So, psi 3 is some other linear combination of e power alpha x and e power minus alpha x. So, we have these 6 constants a prime, b prime and c and d, and we have to choose these 6 constants in such a way that all the conditions that we impose on wave functions, they should be satisfied. And one of the most important conditions that a wave function should satisfy is that it should be normalizable. This follows from the probability interpretation of the wave function. Max Born said that mod psi square dx is the probability of finding the particle between x and x plus dx, and probability should all add up to 1. So, integral of this should be equal to 1, which means that any wave function you write mod square of it, when I integrate it from minus infinity to plus infinity, I should get some finite quantity. So, if the integral is to be finite, then I also have to demand that integrand also should be finite. If the integrand diverges, integral will definitely diverge, because after all integral is the sum of different integrands. So, condition of normalizability leads to the condition that at every point the wave function should be finite. So, in region 1, if I keep both a term as well as a prime term, then I will run into trouble, because for extending to minus infinity, which is in region 1, that a prime term will diverge. So, the requirement that wave function should always be finite compels me to put a prime equal to 0. Similarly, for region 3, extend to infinity is a point there, and the term with the b prime, that will blow up as extends to infinity. So, finiteness of the wave function compels me to put b prime also equal to 0. So, the behavior of the wave function at x equal to plus infinity and minus infinity, they determine that a prime and b prime are both 0. How about at x equal to 0 and at x equal to L? You see that the potential is abruptly changing from u to 0 at x equal to 0, and at x equal to L it is abruptly changing from 0 to u. So, how should the wave function behave at x equal to 0 and at x equal to L? These conditions will determine the other 4 constants a, b, c and d, and also they give us the quantization condition. Now, you see the Schrodinger's equation for psi 1 and Schrodinger's equation at psi 2. So, there is a second derivative in the case of psi 1 and second derivative in the case of psi 2. They are different, but psi 1 and psi 2 meet at the point at x equal to 0, which means that the second derivative there, it has a discontinuous change. It is going from u finite value to potential 0. So, there is a discontinuous change in the potential at x equal to 0, and Schrodinger's equation says that that implies a discontinuous change in the second derivative. Now, if you look at the behavior of functions and their derivatives. If there is a discontinuous change in the second derivative, it means first derivative has to be continuous, but there is a kink in the first derivative. The slope of first derivative here and slope of first derivative here, they are different, but they should be continuous. If the first derivative is continuous, then the function itself should be continuous. So, this is an important difference compared to the infinite potential well. In the case of infinite potential well, at x equal to 0 and at x equal to L, the second derivative again had an abrupt change, but that abrupt change is an infinite change. Because the abrupt change is an infinite change, we argued that the first derivative has a finite change and the wave function itself has a kink. But here the second derivative has a abrupt change, which means first derivative has a kink but is continuous and the function itself is continuous, both at x equal to 0 and at x equal to L, and I have written those conditions in the equation form. Now, if I take the forms I have derived before for psi 1, psi 2 and psi 3 and substitute in these conditions, I get the following 4 equations. Continuity of the wave function at x equal to 0 means A is equal to D. Continuity of the wave function at x equal to L means C times sin kl plus D times sin kl is B times exponential minus alpha L, and continuity of the derivative at x equal to 0 means alpha A is equal to Kc, and continuity of the derivative at x equal to L means Kc cos kl minus Kd sin kl is equal to minus alpha b exponential minus alpha L. So, we have these 4 equations, and in principle we can try to solve them to get A, B, C, D. Remember, there is also the normalization condition which we have to satisfy. If I divide the third equation by the first equation, we get C in terms of D, and already we had A in terms of D. Now, if you divide the fourth equation by second equation, you have that complicated looking formula alpha by k cos kl minus sin kl divided by alpha by k sin kl plus cos kl is equal to minus alpha by k. So, what is the meaning of this equation? Looks very complicated, but what is the meaning of this equation? Before we see that, let us also remind ourselves what alpha and k stand for. Remember, if you see few slides ago, alpha square is 2m times u minus e, the whole thing divided by h cross square, and k square is equal to 2me by h cross square, which means alpha and k are not independent, but together they are bound by this constraint alpha square plus k square is equal to 2mu by h cross square. So, I have this one constraint between alpha and k, and if you look at the boundary conditions, they give me a different condition between alpha and k. So, I have two different conditions on alpha and k. Remember, alpha is a function of energy and k is a function of energy, and we find that these two conditions both of them can be satisfied only if the energy takes some specific values. If you have some arbitrary value of energy, you cannot satisfy both this alpha square plus k square is equal to 2 mu by h cross square and the other complicated looking condition. Another way to look at it is think of alpha and k as two variables, and this alpha square plus k square is equal to 2 mu by h cross square. Strictly speaking, it defines a circle, but we limit ourselves to positive values of alpha and positive values of k. So, it defines a quarter of a circle in the first quadrant. And this equation, it is a much more complicated equation, but this defines another curve. So, for a given k, I substitute in this equation and I can figure out the corresponding alpha. So, this equation gives me a different curve in the alpha k plane, and the intersection of this quarter of a circle and this other curve, that is when both the equations are satisfied, and that is the point which gives me the corresponding energy of that solution. Now, the question is, how many such points are there? That depends on the height of the potential well u, how big this quarter circle is, and depending on that, I may have one solution, two solutions, three solutions, four solutions, etc., etc. It depends on the depth of the well. But important point is that these two conditions, alpha square plus k square is equal to 2 mu by h cross square, and the other condition which I am getting from the satisfying the boundary conditions at x equal to L, these two conditions together give me the quantization of energy in this problem. Explicitly calculating what this energy is, it is quite complicated, and as I told you, you can solve the problem using either graphical techniques or by numerical techniques. But the wave functions themselves look like this. The first three wave functions are drawn on the left hand side and the corresponding probabilities are drawn on the right hand side. And you note that just as in the case of the infinite potential well, the lowest energy state, it has no node and it is symmetric about x equal to L by 2. The first excited state, it has one node and it is antisymmetric about the point x equal to L by 2, and the third state, that is the second excited state, is now symmetric and it has two nodes. So, and if we, in this case, this well has only three solutions, but if it is a deeper well and there is a fourth solution, that would again be antisymmetric. What are the energy eigenvalues in the case of finite potential well? The exact calculation, as I already mentioned, it is a bit complicated, but we can do some kind of approximation to make a reasonably good guess as to what the energy is. You look at the figures on the left hand side of the wave functions. In the case of the infinite potential well, the wave function is exactly 0 at x equal to 0 and at x equal to L, and outside the well the wave function is identically equal to 0. But here you see that the wave function actually is penetrating outside the well, it is non-zero outside the well, which means that there is a non-zero probability to find the particle outside the well. So, we utilize this analogy with infinite potential well, and we introduce this concept called delta penetration depth, which is equal to 1 over alpha. And you can see from these figures that if the distance from the well is greater than delta, then the wave function falls off to 0 very rapidly, it falls off exponentially fast. Therefore, we can think of the width of the well is 0 to L plus delta on the left hand side plus delta on the right hand side. We approximate this as a infinite potential well with width L plus 2 delta and estimate that the nth order energy is n square pi square h cross square divided by 2m times L plus 2 delta whole square. And you find, if you work it out actually, you will find that this approximation works very well for n equal to 1 or 2, but at larger values of n, the E is becoming higher and higher, and when E becomes very close to U, from the definition of delta, you see that delta tends to diverge in that case, and this approximation then does not work. But if you are ever trying to find out the energy levels for a finite potential well, to estimate the ground state energy and maybe the first excited state energy, you can use this approximation to get that. Now, let us switch gears a little bit and talk this problem of consider the problem about simple harmonic oscillator and how to solve this problem in quantum mechanics. By the way, this problem of simple harmonic oscillator is the most famous problem in quantum mechanics. Some may say after the problem of hydrogen atom, but some people would say no, it is the most famous problem. But there are various important aspects to this problem, and this simple harmonic oscillator is used again and again in different contexts of quantum mechanics. So, it's one of those problems which people almost have fallen in love with, so to speak. But one thing which is of interest here is the beginning of quantum idea. If you remember, the quantum idea originated with Max Planck when he was trying to study black body radiation, and so you have the black body which is radiating energy, and to consider the black body in equilibrium with the radiation at temperature T, Max Planck pictured the black body, the walls of the black body to be made up of oscillators which are emitting and absorbing energy, and then he said this emission is taking place in units of h nu. So, quantum mechanically speaking, an oscillator should have energy levels given in terms of h nu. So, now the question is, if we try to solve Schrodinger's equation using harmonic oscillator potential, do we get the quantization condition En is equal to nh h bar omega or nh nu? The answer is yes, but the actual solution requires quite a lot of algebra, which I am not going to do here, but I will give an outline by which we look at the ground state energy and the first excited state energy. Well, before we look at the quantum mechanics of a simple harmonic oscillator, let us consider any arbitrary potential, and it will vary with x, it may have some minima and some maxima, etc. And this is a very famous theorem from classical mechanics, that a system will be in stable equilibrium if it is at a potential minimum, whereas if it is at a potential maximum, then it is a unstable equilibrium. Well, let us assume that I have a potential which has a minimum, and I do a Taylor expansion of this potential around the minimum. When I do that, the potential has the form value of the potential at the minimum, which is a constant, and you know that if I change a potential by a constant, the dynamics does not change. That constant potential, it has no role. Then I have the linear term x minus x minimum times dv dx at x minimum, but for the condition for minimum is that the first derivative should vanish. So, the first, that linear term x minus x minimum is not there. The x dependence comes only in the quadratic term, x minus x minimum whole square by 2 times d square v by dx square evaluated at x equal to x minimum. And we know that for minimum d square v by dx square is a positive quantity. So, we have a potential which is of the form half times a positive quantity times x square, where x is the displacement from the minimum. That is what we call oscillator potential. And if we write the time independent Schrodinger's equation for it, it has the form displayed in the slide. D square psi by dx square is equal to 2m by h cross square multiplied by m omega square x square by 2 minus e, the whole thing multiplied by psi of x. And as I told you, solution is quite complicated, and if people are interested, you can consult books on advanced quantum mechanics. One book which I use when I teach quantum mechanics course is Principles of Quantum Mechanics by R. Shankar, and this problem of simple harmonic oscillator is discussed in chapter 7 of Shankar's book, but you can consider any other advanced book such as Sakurai or Merzbacher, Gottfried, lot of good books are there. You can consider any one of them, and the solution to harmonic oscillator problem is given there. However, here we try to find the ground state by making some educated guess. How do we do that? Well, we actually try to find the ground state wave function by looking at its behavior as x tends to plus infinity and minus infinity. So, in that limit x tending to plus minus infinity, that potential term m omega square x square by 2 will be much larger than the energy. So, I ignore the energy, then my differential equation becomes d square psi dx square is equal to m omega square by h cross square times x square times psi. I define a quantity called alpha, that is m omega by h cross, then my differential equation is d square psi dx square is equal to alpha square x square psi of x. Now, I have to do some inspired guesswork or trial and error, and if you do so, you find that the function psi naught, which is n naught times exponential minus alpha x square by 2, that satisfies the differential equation, and n naught here is some constant, and I fix it by the normalization condition that mod psi square integral of mod psi square dx should be 1. And I substitute this guess of wave function in the full-fledged Schrodinger's equation, and I get the corresponding energy eigenvalue 2m E naught by h cross square is equal to alpha, which of course is m omega by h cross, which means the lowest energy eigenvalue E naught is half h cross omega. And let us briefly look at the symmetry aspects of this wave function. The potential itself is symmetric under the transformation x going to minus x, and we note that the ground state also has the same symmetry and it has no nodes. Now, just as in the case of infinite potential well, we demand that the first excited state should be antisymmetric. So, for that we make the following guess regarding the wave function. The first excited state wave function, we take it to be n1 times x times exponential minus alpha x square by 2, and you can see easily that this function is antisymmetric when I do x to minus x, and also it has one node. Once again, I substitute this psi 1 in the full-fledged Schrodinger's equation, and when I do that, I get the corresponding energy eigenvalue here to be equal to 3 by 2 h cross omega, which you notice is the minimum energy E naught, that is half h cross omega plus h cross omega. So, the difference of energies between the lowest energy and the first excited state is h cross omega. So, it is sort of pointing along Planck hypothesis. But if you look up Shankar or any other book, you will find that the nth order energy eigenfunction psi n of x is some normalization constant nn times h n y, where h and y are some functions exponential minus y square by 2, where the variable y is square root of alpha multiplied by x, that is the variable y, and nn, as I said, is a normalization constant. And these functions h n of y, they are called Hermite polynomials, and they have some very nice properties. And by substituting these functions in the Schrodinger's equation, we can get the energy quantization condition that the nth level of energy, it has value n plus half times h cross omega. So, Planck said En is nh nu, that is nh cross omega, but here we have an extra half, that extra h cross omega by 2. This is called vacuum energy or 0 point energy. What is the physical significance of this? Well, there is a lot of debate about that, so we will not really go into it. Anyway, as far as Planck hypothesis is concerned, we are interested in energy emissions or absorptions, which means that the differences in energy are given by n h bar omega. In this figure, we see the wave functions, on the left hand side we see the wave functions, and on the right hand side we see the probability distributions. For psi naught, we have a symmetric wave function, and psi 1 you have an antisymmetric wave function, psi 2 symmetric, psi 3 antisymmetric, etc. Also psi naught there is no node, psi 1 there is one node, psi 2 there are two nodes, psi 3 there are three nodes, etc. And you see the probability. In the beginning it does not look anything like an oscillator, but by the time you come to psi 3 square you begin to see that oscillator looking pattern. More probability at the end points and less probability at the center, and that is what we expect for an oscillator. Oscillator at the end points has very low velocity, so it tends to spend more time at the end points, whereas passing through the equilibrium it has essentially kinetic energy, so it moves very fast through the equilibrium. So probability of finding it in the middle is much less, and if you make a plot for some psi 10 or psi 20 square, you find that the probability would look like this, with more probability at the end points and low probability at the central point. So with this I have come to the conclusion of my share of lectures. Professor Aftab Alam will take up the baton from here, and he will discuss three important topics. First topic he will discuss is scattering. In my part of the course I have discussed the so called bound state problems. So there are boundaries and the particle remains within the boundaries, whereas you have situations if the energy of the particle is high enough, it can escape those boundaries and it can go from minus infinity to plus infinity, and that is what happens in such a situation. We describe the motion of such particles through scattering, and Professor Aftab will cover scattering first, which leads to an extremely interesting and almost a magic like thing called tunneling. You will see that in the next few lectures, and then he will very briefly discuss the concept of quantum statistics, and then he will go to discussing how to utilize our knowledge of quantum mechanics to understand the properties of solids. That is one of the most important applications of quantum mechanics. He will spend 4 or 5 lectures discussing this applications aspect, which will finally conclude the course. Thank you for joining us, and we will post these lectures very soon, and we will also post the necessary supplementary material. Thank you.